This is a little video on addressing modes. As you remember here, just a quick review. We can look at this slide here. Here's how it works in C and C++ on the left, and how it works in assembly. So if you have int, cat, dog, if you're using register mode, you move from one register to the other. This would be especially true if you declared dog and cat to be registers. Then if you have something like an array, here on the left we have a character array table with 100 elements in it. And over here you can see we're moving table R4 into R5, which means basically we're taking whatever numbers in R4, that's our index for the array table, and putting it in R5. And you can see it's a .b move because we're moving bytes, because it's a character. That's called indexed register addressing mode. And then we have indirect register, and this is most analogous in C to a pointer. So basically it takes whatever number is in R6, and that's the address, and it goes out to that address and grabs the data from there and moves it to register 5. It's doing this in a byte-wise way because cow is a pointer pointing to a character, which is a 1 byte. And now we have auto increment indirect. And notice here we have the same thing we had before, but there's a plus appended onto the register 6, which indicates that it increments register 6 after the operation. And that's similar to what you see over on the left for C, cat equals star cow plus. And then we have immediate, we're putting an actual number into cat, and over here we're moving immediate 100 into register 5. And then we have absolute, so basically we're loading cat with whatever's in the address at address 100. And over here in absolute, it's an ampersand 100 instead of a star 100. That means whatever's in the address 100, move that into R5. And lastly, we have symbolic, cat equals dog, and we can do that with assembly, move.w dog into R5. And basically, that works when you've assigned dog using a .equate directive, assembler directive. Now what I'd like to do is I'd like to look at this same kind of thing in our own little program in Code Composer Studio. So I've put together a Code Composer Studio program here that says some of that kind of thing in it. And let's look at this main program here so we can understand what's going on here. So I've defined a global table array, and I put 119, 120, 121, 122 in it. It's a character table, so those are bytes. In ASCII, those are W, X, Y, and Z, or what those numbers are. Or in hex, it's 0x77, 0x78, and so on. And then I also declared a global pointer to a character called cow. And then I've got my main program here. The first thing we do is turn off the watchdog timer. And then I'm just basically assigning some variables, unsigned int to dog, register int to cat, int to zebra. Zebra was actually never used down here, it says, but seems like I do say zebra is table of dog plus plus. I better make sure we've compiled this. It looks like we did. Then I have just some things going on here. Dog equals 2, cat equals dog, cat plus plus. And then while dog less than 4, cat equals table of dog, and then increment the dog. And if cat equals the W ASCII character, increment cow, the pointer cow. And star cow equals table of dog. And then zebra equals table of dog plus plus, so we're going to increment the dog after that. And then cat equals star cow plus plus, and then I return 0. So get rid of an extra space there we don't really need. And I'm going to compile this thing just to make sure I've compiled it and it works okay. You can see some warnings over here. The standard one about live math not being able to be found. Zebra was set but never used. And the project was created using a version of C compilers not currently installed. Yeah, I started this example last year, so we were using an older version of Code Composer Studio. Let's debug it. So we're debugging here. This is the standard debugging perspective. You can look at different perspectives up here in the window, go down to perspective, and you can pick one there, or you can just go over here. I want to look at a special perspective that I created by dragging these windows around and using the view up here to grab what I wanted. You can get the debug window, the memory browser, registers, expressions, variables, the disassembly, breakpoints, and modules. So I want to look at that. I want to look at that perspective because I've got it set up to give us more information here. I'd like to open the core registers. Those are the 16, R0 through R15, R0 being the program counter. Over here we have the disassembly. Now I have actually, if you go back to the edit perspective here, I did set some build settings to try and get it not to optimize anything. You can look at the optimization here, and it says it's off. But that doesn't mean the C compiler, when you do a program like this, you got to be careful, because basically you will find that the C compiler is still kind of smart, and if you made a program that you don't need something, it probably won't do it. Like I noticed previously that I had something like this, table of dog plus plus, but I never used dog again in the program, and it didn't bother incrementing it. So you got to be careful, when you're comparing C code that's kind of cooked up like this to the assembly that the assembler generates, or the C compiler generated this assembler here. And sometimes it's a little bit more optimized than you would expect. In other words, each line over here doesn't correspond to each line over here. In fact, here's the main right here, and then it has this watchdog thing. That's the first thing it did. And the dog equals 2, that's there. The cat equals dog is there. But you don't see things like int register cat. You just kind of have to figure out down here when I say cat equals dog. Here's dog equals 2. It's moving immediate 2 onto the stack. So basically that tells me that the unsigned int dog is on the stack. And then it moves down here when it does cat equals dog. It moves what's ever at the stack. In other words, this is indirect addressing what's on the stack into register 15. So register 15 must be being used for that register integer that I put over here. I assigned it to a register. When you put the register word, a special word in front, if it can, it tries to assign that value to a register. And sure enough, it did here. Then if you look at cat plus plus, that does look like it incremented register 15. because remember cat was the register. So that seemed like it did what we expected. Here's the wild dog less than 4. So it compares immediate 4 to dog there. And if it's a JHS, so that means if it's jump higher than, it jumps out of this routine down to this label here, C3, $CL3. So down here it jumps right out of the whole thing here, right down to this star cow business here. You can see the star cow equals table of dog there. That's the comment, C comment above this label where it's going. So you can see that happening here. And so then, if it wasn't greater than 4, it does this cat equals table of dog plus plus. So here that we have that. We're moving the stack pointer, and notice cat was the register. It was register 15, but we're moving, remember, it's moving this whatever's in the stack pointer to register 14, and then it moves register 14 to register 15. So remember cat was register 15, so basically these two guys, I'm not sure why it did both of them right off, except it's going to use register 14 down here. So then it took register 15, which was cat, and moved that onto the stack, and then it did moved a table. 2400 was table, so if you look at 2400 over here in the memory browser, 0x 2400, you'll see, yeah, there it is, table. It's 7A, and you can look on this in different ways. You can look at it at TI hex style, it's 7778 79 7A, or you can look at it, in C style, and now you can see it's a little bit different. You can look at 32-bit signed in, or you can pick what how you want to look at it. Here's 16-bit, and that you can look at the memory in different formats there. So anyway, 2400 is table. That's where table is. So 2400, and it's using indexed addressing with R14, and R14 was, remember, they moved the stack pointer in here, so the stack pointer, remember, was pointing to dog, so they took dog here, that's dog right there, and it's taking this dog right here. R14 was dog, and it's getting the dog, table of dog, and it's moving that into 15, which was cat, and this other stuff is supposed to increment dog, I think, although I'm not sure. It says dog plus plus there. Let's see, dog was the stack pointer, so it incremented R15 and then it put it on the stack, so that incremented it. So anyway, you can see how that works there if you look closely. And like I say, be careful here, because sometimes when it doesn't need to do something like that, it might not. So using this to actually understand the assembly is a little bit fraught with problems. So then we have if cat equals W, you want to increment cow, so it compares W, which is 0x77, to what's in R15, which was cat, and then it jumps not equal down here. Otherwise, it increments cow, or what the cow is pointing to. Increments the address cow is pointing to. And we can execute this stuff bit by bit. If you want to in assembly, you can you can, oh, I gotta turn this alarm off, I'm sorry. You've got to, you can go up here and use the assembly and kind of watch things. So let's just kind of do that. So you can see right there, it did the, it incremented the PC, and the stack pointer is initialized, and the status register got changed by that operation. Now we just shut off the watchdog timer, and now we're going to move 2 into the stack pointer. So if you wanted to, you could look at the stack here. See, the stack pointer is 43FA, so if I go to 0x43F, oops, FA, oh not YA, FA. So if I go there, and if I execute this one more time, we should see a 2 appear there somewhere. Yeah, there it is. It turned into a 2. You see that right there. So that moved 2 onto the stack. Now we can move that 2 into register 15. So watch this dude down here. So we do that. Boom. Yeah, it changed to 2. And now we can go down and we can look at this comparison. We're going to compare 4 with whatever's at the stack pointer there, which is 2. And if you want to look at the results of this, you can look at the status register right here. And so here are the flags. This is the overflow flag. These guys are special constant flag. These are for the oscillator on and off, so we don't need to, we can ignore those. This is global interrupt enable. Then we have N for negative result, Z for 0 result, and C for carry. So really we're looking for whether we get a 0 result because it does this compare. That's kind of like a subtraction there. So let's watch it and see what happens. So we go down and we're going to do the compare there, and notice it did come up with a negative result, so it just jumped higher than, and it jumps back up here, and it's going to keep going through and incrementing that guy until finally, you know, it gets up to 4, and then we're going to get out of the while loop, and now we're going down here and we're incrementing. We're looking where what cow is. We're putting, we're moving here. Let's move this so you can actually see what's going on here above there. We're moving table of dog into the cow variable, what cow is pointing to here. And that's done in this little business back here. Here's table of dog, and it's going into cow. So once we hit this guy, then we're going to do it this next time. And we did the zebra thing. And you know, you could watch all this stuff over here in this window too if you wanted to. You could see what's going on here in the either by scooting this over, you know, and see what you're changing those to, or you could you can double click on this thing right here, or maybe it's this guy right here, maximize, and you can see just exactly what's happening to those in this way of looking at it too. So anyway, what I'm trying to show you here is that it's possible to watch down through the C code and compare it to the disassembly, you know, the assembly code, the disassembly of the C, what the C compiler made. You can see it doing all these kind of things. This is another indirect incremented or indexed addressing mode down here. So play with this. You can make up your own little C program like this and try it out. It's not that hard. So with that, I think we'll say that's good enough for this video.